Welcome to ESA's Countdown to Asteroid Day Live. I'm here at ESA in Italy to warm you up with a little bit of light terror as we introduce the riskiest asteroid known to humankind. In August last year, an asteroid was discovered that soon became the riskiest space rock that we knew of. At 50 meters wide, the asteroid, known to scientists as 2021 QM1, was predicted to have a chance of impacting Earth on the 2nd of April 2052. I'll introduce you to the asteroid experts who are looking up, following this asteroid and protecting us from any harm. Or maybe not. Frascati near Rome is home to ESA's Near-Earth Object Coordination Centre, the NEOCC, where a small but dedicated team spend their time tracking down risky asteroids. I want to know what happened last August when asteroid 2021 QM1 came onto their radar, and I've heard a man called Marco the Asteroid Killer McKelly could tell us more. Marco, the Asteroid Killer. I was hoping you could set the scene a little bit about when the world discovered this risky asteroid. What happened? How did it feel?
Yes, 2021 QM1, it's the asteroid we are talking about, was discovered last year, the end of August, by one of these automated telescopes called automated surveys in the US, in this case in Arizona, called the Catalina Sky Survey. What these telescopes do is every night they scan the sky looking for new asteroids that have not been seen before. And on that particular night, I think on the 28th of August, they happened to find another new asteroid. In itself, this is a pretty routine event. The surveys are actually pretty good at their job, so every night they find a few dozen new asteroids. So as of that day, we didn't know anything peculiar about this object. It was just one of the many new discoveries of that night. What typically happens is that when these surveys discover something new, they immediately send the data to a center called the Minor Planet Center, which is in the US, in Massachusetts. And the data is immediately made public for everybody to use and to analyze. This happened for this object, as with all the other ones. And within a few hours, other telescopes around the world started doing what we call follow-up. So observing the asteroid again, and getting more and more positional data of where the asteroid was moving in the sky. This went on for a few days, as it usually does, and at a certain point, the people here at our center got enough data to start computing an actual orbit of this asteroid, so just computing the path of the asteroid in the solar system. And when this happened, something for the first time started being a bit more unusual, because this object showed an orbit that had a possibility of coming close to the Earth. And in particular, it showed the possibility of having an impact with the Earth in a few decades from now. And this is exactly when we start paying particular attention to an object, because it becomes a bit more unique, a bit more unusual.
So you decided you needed some more data, you need to observe it, and then what happened next?
Well, this is a pretty routine process. And when an object like this gets a possible impact in the future, we, and not just us, like the whole world, tries to observe it for the following days and weeks and months. However, this happened for about a week. People kept observing this object. But unfortunately, unusually, well, sometimes it happens, but not all the times, the object moved in the sky towards the direction where the sun is in the sky. And of course, since the sun is bright and it's up during daytime, when an asteroid moves close to the sun is when we cannot observe it anymore. So in about a week after discovery, due to this motion of the asteroid in front of the sun, we could not observe the asteroid anymore. Unfortunately, it's a pretty small asteroid, so it's about 50 meters in size. So by the time it moved away from the direction of the sun in its motion in the sky, well, it had receded too much from the Earth, and it was too faint to see. So for the following few months, it was now invisible just because it's a tiny object and it's way too distant from us to observe even with the biggest possible telescopes. So it kind of ran away from us before we had enough data to say something conclusive on it. We were stuck in a kind of limbo with the object still being possibly in an impact course. We are, of course, not sure it is in an impact course, but we could not exclude it with the data we had.
And let's say, worst case scenario, it is on an impact course. What kind of damage could a 50-meter object do?
Well, this is actually pretty easy to estimate because it has happened in the past. And the type of damage an object of this size can do on the ground depends on what it's made of. Asteroids can either be rocky or metallic. And fortunately, we have two real-life examples of either type. If this object happens to be metallic, the easiest example we can think of is a crater that is pretty famous in Arizona. It's called the Meteor Crater. It's a couple of kilometers in size, and it's a big hole in the ground in the desert. And that was carved by a roughly 40-50 meter asteroid that hit the desert of the southwest of the United States a few tens of thousands of years ago. So that's what it would do if it's metallic. It would release all the energy upon impact on the ground and carve a big hole in the ground, and of course cause destruction for all the immediate vicinities of that. If, on the other hand, it happens to be rocky, and we don't know that, because we don't know the composition of it at the moment, it will likely go through the atmosphere and probably explode in the atmosphere while getting subjected to the pressures of the entry into the atmosphere. So it will likely explode somewhere up in the atmosphere, maybe 5, 10, 20 kilometers up, and it will cause a shock wave that will propagate down to the Earth, down to the surface, and likely cause pretty significant destruction on the Earth. And here we have an example in 1908 in Siberia. Something that is now known as the Tunguska event happened, and we think it was an explosion of, again, a roughly 50-meter asteroid that just disintegrated in the atmosphere. And the result was a radius of 70 kilometers of Siberian forest was completely destroyed by the impact. So it's not a world event, it's not a calamity that will affect the planet, but it's a significant event. And that's why we care about asteroids of this size.
What a cliffhanger! It seems the experts at this point were in a sort of asteroid limbo. But I've got to know, what next for this rock? Will it strike? They need more data, but how will they get it? I'm meeting NEOCC astronomer Dora near a very nice model of an important telescope. Hi, so Dora, what is this strange-looking object?
Here we're standing in front of the model of the FlyEye telescope. This is a telescope that ESA is building to survey NEOs. It's going to have a 1 meter diameter. And the interesting thing about it is that it has 16 cameras that will split the light so that we can see a much wider field of view. So we can see a lot more asteroids a lot sooner, so have a better chance of detecting a potential impactor.
That sounds much needed. And is this the kind of telescope ESA's always using? Does it have any other telescopes?
ESA is using several telescopes around the world. We have our own telescopes in Chile, in the Canaries, in mainland Spain, and we have contracts around the world with several institutions where we can use their telescope at a very short notice. So if we see something coming, we'll be able to track it down within minutes. At some point, there's always going to be dark, and at some point, the weather's always going to be cooperating. Mm-hmm. So through these collaborations, the sun is never going to rise on ESA's network.
Yeah, great. So it's always dark somewhere on the planet, and ESA benefits from that. That's really interesting. And so this kind of telescope, is this what we're going to be using for our very own risky asteroid that we're following?
No, our asteroid that we're following is much too faint. This type of asteroid is designed for the more imminent impactors. To observe something much fainter, we're going to have to use a telescope that's much, much larger in size to collect more light. And this will be the VLT.
What's the VLT?
The Very Large Telescope. It's an 8 meter class telescope located in Chile.
Great name. As our risky asteroid gets harder to see, only the Very Large Telescope will help us find it. With the help of some unusual shapes and a rather big heart, Juan Luis explained why our asteroid is so hard to track. Hi, so Juan Luis. I've already spoken to Dora, who told us that the VLT is very important. Why?
Let's try to explain that. First, let's have a look at this animation that we have here, where we see the inner part of the solar system, and we see the Earth orbit, the Sun, and the inner planets. And we also see here a blue trajectory, which is actually the one of the asteroid. You see here 2021 QM1, which is our object. Now we will try to understand why we need to use a VLT in this situation. Imagine that we, instead of having the representation that we just had, we freeze the Earth in its motion. So instead of going around the Sun, we just freeze it there. And we try to see what the asteroid makes in the space. And this is the kind of representation that we see here. So this is the Sun again in the middle. This is the position of the Earth, where you see this one here. This is 1 astronomical unit, which is the distance from the Sun to the Earth. And here you see how that trajectory, which was initially an ellipse, when you have this fixing of the position of the Earth, how it goes around the Earth. And what you see here is this heart shape here that tells us what was the detection area that the telescope that found the object had at the moment of the discovery. And you see that the object is inside that region, so it was observable to this telescope. The region that is outside this heart is not observable for this telescope. So the object was found there, but as Marco commented, just a few days after, it went into the direction of the Sun, so it was not visible anymore from the telescopes on Earth. And it started to move into this, let's say, strange loop. And it's now coming to this area where it is the time where we are now. So when we have a telescope which is much more powerful than the one that discovered this asteroid, as for example VLTs, we're able to reach much larger distances in order to detect the asteroid. And as you see, the asteroid moving to this direction, which was very far from the Earth. Recall that the Earth is here. And now with this telescope that has a much stronger detection limit, we're able to try to find the object in this area here, which is what we call opposition. So here it is where we are trying to detect now the asteroid. Okay, this is what we call the heart of observation. And what happens is that the object will transition this area that the VLT can observe. And it's, as I said, the area which is inside this heart, the one that will be observable. And this is an interval of time of a few weeks where the VLT will be able to observe this object. So as you see, after this observational period here, the object will slowly move out of the imaging of the telescope. I have changed the parameters of the trajectory, which are compatible with the impacting trajectory. And now you see that the branch that was going above the Earth in this representation, now it heads directly to the Earth and then impacts. And this would mean that the object would, as it happened with the Chelivens case, that it would impact the Earth from the direction of the Sun.
Direct to the heart.
Direct to the heart.
Okay, but we find out soon.
We will find out soon whether we can exclude the impact solution or not.
I didn't expect such poetry from asteroid experts. Since our chat, breaking news came in. The team has aimed the VLT at a part of the sky they expect our asteroid to be, and the images are in. Before we see them, I found Laura, who explains the potential consequences. So, we have these observations that may or may not be our asteroid. What can you tell us about the risk?
Okay, if these observations are correct, we can say that the impact for the 2052 year is out. So yeah, in this case, the object will go out from the risk list.
And how is it that you calculate the risk of an asteroid? How do you determine its trajectory?
Okay, we have to start to the orbit determination, because this is the first things that we do. And explain in some way what is the uncertainty, because it is a really important concept for our work. And if you like, I can draw something.
Please.
Okay, so if it is the Earth and we are here, so the observatory is here. For example, the observer do these observations in the sky. So we need at least 3 observations to determine an orbit. At least 3 at different times. This is really important. So as you can see, we can draw a trajectory, but we are not sure that it is the right one, because also this one is correct, and so on. So what we can say in this case, that we have a trajectory with an uncertainty region. So it is, for example, if we say that it is the most reliable trajectory, there is an uncertainty that it is usually an ellipse. Okay, so this is the uncertainty. So the next observation can be here, here, here. We don't know. So the observer try to find another observation in this region. And for example, he find this one. So we can redefine the orbit in this way, and so on. It is an iterative process. Okay, but the important thing that I want to underline is that every time the uncertainty is shrinked. So every time observations are added, we can redefine the orbit and have more precise orbit. So once we have this orbit and its uncertainty region, we can sample this region in the sense that, okay, if this is the region, the uncertainty region, we can say, okay, here there is the object, but it can be here, 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 and so on.
Yeah.
So we have what we call virtual asteroids, because we are not sure that it is exactly one of them.
Which is the real one,
okay. And propagate the orbit, its orbit for 100 years, and see if one of these objects, these virtual asteroids, impacts the Earth. This is the, okay, in a simplified way, this is the algorithm.
Fascinating. Thank you.
Thank you.
Oh, Laura left her notebook. So, if these latest observations reveal our asteroid, it seems Earth would be safe in 2052, making these some of the most important images the NEOCC team have taken in years. Enough suspense, we drop in on a call with 2 old friends, Olivier and Marco. Will the asteroid killer strike again?
Hey Marco, can you hear me?
Yes, I can hear you. Hi.
Great.
How are you doing?
I just sent you the images of QM1. You remember the nasty one?
I did. I got them, and it's really promising. What do you think?
I believe it. I believe it. But remember, this is the most threatening asteroid at the top of our risk list. It's the faintest we ever attempted to observe.
Indeed it is.
The field of view where it was horrible. We were almost in the Milky Way. It's full of stars. I mean, it's on the original data, you just see stars everywhere.
Yeah,
but I think that the magic image subtraction technique kind of worked really well. And you see on the image that dot, I believe it. It is, that is an asteroid. That is a real asteroid.
To lend more reason to believe it is that we have a whole image in front of us, but it actually happens to be on the line where our asteroid could have been. And that is an interesting, it would be too much a coincidence if it weren't actually our asteroid.
Okay. Yeah, because I looked at the whole image. I don't know where the reasonable part is, and what you're saying is that I found it where
Exactly.
it was supposed to be.
It can only be on a line, and it happens to be on that line, and you did not know about that line before doing the search. So
Yeah, no.
exactly. So that I think
Yes.
is a convincing proof. I think it's a convincing some evidence that it's indeed our object.
But I think this object is really the perfect example of what we can do with a VLT.
Indeed, it is.
It's the VLT is such a narrow field of view, but in that field of view, nothing can hide.
Indeed.
So if we can be sure that it's in the field of view, we just hammer it down and go deep, and there basically it's the best telescope in the world for this kind of thing. So we got.
And this was just perfect because the uncertainty in the sky, so the area in the sky where it could be, was basically just the size of our field, so we could cover it all. It's just, it was the perfect test case of what this amazing telescope can do. So.
Okay, I measured the brightness, using the stars in the field as reference, and I get a magnitude of 27.2.
This is amazing. It will be the faintest ever we've ever got, right?
I think it's the faintest asteroid we ever observed.
Yeah, possibly even the faintest anybody has ever observed.
To summarize, we have secured the recovery of QM1.
We have one night.
I'm convinced that the object is really an asteroid, and you are convinced that it is our asteroid.
Yes, that I can say. If it's an asteroid, it's our asteroid for the way where it falls in the field and the way we combine the images. If that's an asteroid, it's our asteroid. I can say that.
Yeah. Yes, and I can quantify how much I'm sure, but it's not a background noise.
That's the only thing.
It is an object. It is real. And then let's talk via email to see when we try to get the confirmation.
Exactly. Let's get in touch with that.
Good.
Perfect. Sounds like a plan.
Okay.
Thank you.
Ciao. Have a nice day.
Bye.
Put the bucket lists away, they've found our risky asteroid. Or should I say asteroid? Or should I say slight blur? Well, if they're convinced, so am I. But I can't help but think this could so easily have gone the other way. For my final stop, I speak to Luca, manager of ESA's Near-Earth Object Coordination Centre, for some what-ifs. Hi, Luca.
Hi, how are you?
Very well. So we've been talking today about our riskiest asteroid 2021 QM1, and it really looks like it's not going to strike Earth in 2052. But if we'd got information that was different, that said it was going to strike, what could we do about it anyway?
So the first thing we would do is to keep following the asteroids in the next 30 years in order to be sure that it's actually impacting Earth, in order to reduce the uncertainty, in order to determine in the best possible way where it would impact Earth. Then there are various international bodies organized by the UN, where we would discuss what kind of measures we could take. There is a more active one, more active approach. In this case, we would build a spacecraft. We will launch it, and in order to hit the asteroids and deviate it from its orbit, from its impacting orbit. That's exactly what the NASA mission DART is gonna do next September. The second option is, let's say, it's more a passive approach. So we will not try to deviate the asteroid. We would just evacuate, alert the local authorities, and alert the area where it would impact. As an example, if we know that the asteroid would impact an ocean or a desert, there is no risk of human life, so probably it's not worth building a spacecraft.
Okay, and you can tell in advance where an asteroid's going to hit on Earth?
We can tell. It really depends on how precise is our knowledge of where the asteroid is. We usually know with a precision of few 100 kilometers. We know that it's gonna hit along this line, for example, and not outside. So the uncertainty is in this direction, but not in the other one.
So this asteroid we're pretty sure is safe, but are there any others out there that we think could be a risk that we're worried about in the next 100 years?
So today we know 30,000 asteroids that are passing near Earth. Again, it's near in terms of astronomical terms. So usually most of them are passing at millions of kilometers from Earth. And we know almost all the asteroids bigger than 1 kilometer. And we know that none of them is impacting Earth in the next 100 years. So in this case, there is no apocalyptic scenario like the extinction of the dinosaurs or like Deep Impact or Armageddon. So in that sense, we are not worried. Indeed, we don't know most of the asteroids that are smaller than a few hundred meters. And especially the ones below 100 meters, we really know very little of them. Statistically speaking, we know that an asteroid of 100 meters, it's impacting Earth about once every 10,000 years. While an asteroid of 10 meters in size is impacting Earth roughly once every 10-20 years. So it is in this range that's where we are really working hard to improve our detection capabilities so that we can be sure that a medium-sized asteroid will not harm us too much.
Okay, that sounds reassuring. And this is all kind of scary stuff if there was an asteroid that was going to strike, and surely it's top secret, no one could really find out about it.
Well, absolutely not. All the information we gather, all the data we gather, all the computation we do, it's publicly available on a website maintained by us. Specifically, we maintain a risk list webpage where we list all the 1,400 objects that we know nowadays that have a minimal probability of impacting Earth in the next 100 years. And in this list, we also mention how big is the asteroid, what is the probability of impact, and when would be the impact date or dates, because sometimes they have multiple impact options.
Wow.
So as well, this, as I said, is publicly available, so people can go there and have a look.
And my final question to you is just, do you sleep well at night working with asteroids every day?
Yeah, I mean, as I said, we have no risk, so in this sense, I have no problem in sleeping.
That's good to hear. Thank you.
You're welcome.
Well, that's the end of a long day. QM1 is still out there, weaving around the solar system, but it now looks rather dull, from a planetary defence perspective. I'm leaving, but ESA's planetary defenders are still here and onto the next asteroid that could do us harm. I've got to say, I find it quite reassuring that there are people whose job it is to look up all the time on behalf of us all.